So to finish chapter 5, we're only doing two sections of it. We're doing the first and last, really. Um, we deal with the concept that is often taught in some Algebra 2 courses. Certainly, it's taught a lot in pre-calculus courses. Not very difficult, but has its share of formulas you have to kind of get familiar with. And that's dealing with arithmetic and geometric progressions, also sometimes known as sequences and series. So, so basically we're going to be looking at, a strings of numbers and trying to find a particular number in that sequence, given its position, and being able to find a sum of the numbers from the first through a certain number of them, given that information. So, again, this basically it's not a very long lesson because there's this formula you have to kind of get used to using and practicing with. So this should be a rather short video, and not take you very long to get through it, except for how long it may take you to work out the examples. So arithmetic progressions, and that's the way they pronounce it. I don't ever knew why. I mean, it's spelled the same way as arithmetic, but for some reason, when you talk about progressions, sequences, series, whichever word you want to use to describe it, they say arithmetic. And it doesn't matter. I mean, but an arithmetic progression is a sequence of numbers in which each term after the first is obtained by adding a constant d to the preceding term. That constant is called the common difference. Now, one of the things that some texts and some courses will go into is they'll first go into what they call a recursive formula, where basically, as long as I know the previous number in the sequence, I can tell you what the next one is just by applying the common difference. Recursive formulas are how these things were initially studied, but very impractical because for me if I want to know what the 100th term of the sequence is, I had to have known what the 99th is, and therefore the 98th, the 97th, all the way down the line. The issue is, that's not really convenient because if I want to know the 100th term of a sequence, I would like to be able to figure that out immediately or as immediately as possible. So what took some time was to come up with what they call an explicit formula, which I could say, okay, if I know where it needs to fall in this sequence, and as long as I know what the first term is, I know what the common difference is, and I know what position I'm looking for in the sequence, I can tell you what number is there. So, and that recursive formula, or that explicit formula, is this here. Basically, that a sub n. Now, the subscript stands for what position it is in the sequence. Equals a. You're going to see some textbooks that actually use sub 1 for that, because that means the first term of the sequence. So you may see some texts, put a little subscript of 1 right here to signify it is the first term of the sequence, plus n minus 1, n being the term in the sequence. You notice that n's right here and right here. So if I know it's like the 50th term, n would be 50. And of course, d is the common difference. So, case in point, if you were given this example, find the 25th term of the following sequence, how would you go about doing it? Take a moment, use the information that's here, and see if you can figure it out, and then we'll go over it. Okay, so, here we just have to gather some pieces of information for ourselves to use this formula. And those pieces of information are the following. I know that a, or a sub 1, is 5. It's the first term of the sequence. I can see as I go from term to term, I am jumping 3.5. Keep in mind that for arithmetic sequences, the common difference could also be negative. I could have a higher value and be going down in value. That is possible. The other one I didn't write in here yet is this term right here. Since I'm looking for the 25th term, that means that n is going to be 25. So when I compute this all out, I know I'm looking for the 25th term of the sequence. A is going to be 5 plus 25 minus 1 times 3.5. And when I work that out, I get that the 25th term of that sequence is 89. So I don't have to figure out I was given 4 terms of this sequence, or no, I was given 1, 2, 3, 4, 5 terms of this sequence. I didn't have to figure out 6 through 24 and then use that to get what 25 is. That would have taken a little bit longer. I mean, this is a significant shortcut. The sum of the terms in an arithmetic progression. There's actually two formulas for this. The formula that your book gives is this one here. So if I'm looking for the sum of the first n terms of an arithmetic progression, with first term A and common difference D, that's the formula that you could possibly use. There's another formula that was given. This formula was actually found by the mathematician Fermat, and the thing that sometimes makes some people feel like they're what their mental intellect is like, and I feel it myself at times, is that this mathematician Fermat came up with this when he was the great old age of 7. And basically, he was one of those kids that annoyed his teachers by asking question after question after question after question, because he always finished his work early and all that good stuff. So basically, his teacher told him to, add the numbers from 1 to 100, thinking it would take him some time to do it. He came up like 2 minutes later saying he did it because he found a formula that came up with it. So, wow. So, yeah, basically the way this works is that the sum is given by n times a sub 1 plus a sub n. So basically the first term of the sequence and the last term, whatever that term is. If it's if you're looking for 25 terms, it's the 25th term. If it's like you're looking for 30 terms, it's the 30th term, whatever. N being the number of terms. If you follow this formula, that would calculate the same thing. These are good for different circumstances. The first one, the one the book is good if the nth term is not known. If I don't know what the last term of the sequence is or I haven't found it, that's the one I want to go with, because that would require an extra calculation. And actually part of the calculation of finding that nth term is in that formula. Whereas if I happen to know what the nth term is already, the second one is also a formula. So if you were asked to add the numbers 1 through 100, you know what the first term is, you know what the last term is. You notice that the common difference doesn't play a role in this because, if you know how many terms that is, and you know what the first and last terms are, that kind of hides the information of what your common difference is, because you can kind of figure that out. I would use that second one. So, depending on how you approach this problem that we have here, find the sum of the first 25 terms of the following sequence. If you notice, that's the same sequence we have in example 1. So, you could use either formula here. So maybe try either formula, try both, see if you could get a calculation for them. But, come up with your answer, figure out what the sum of the first 25 terms are, and then we'll go through the possible answers. Okay, so as I look at this particular problem, I do know that, if I was approaching it and I hadn't done example 1, I would look at this and say, okay, n equals 25, d equals 3.5, a sub 1, or a, depending on which formula you're using, the first term is 5. Now, if this is the only problem that was given, if I was to say, hey, here's the problem, we didn't do the previous example, then I would probably go with this first formula. Because I don't know what the last term of the sequence is, and I had to calculate it. It just so happens, though, in example 1, we did calculate what a of 25 is. And we know that's 89 based off of the last thing we did. So with these circumstances, it's actually easier to use the second formula. And if I use it, I'm just plugging the 25 in for n. A1, the first term is 5. The nth term, or 25th term, is 89, all divided by 2. And when I work that out, I get 1,175. Just to show you, though, if we had not done example 1 first, I said the first formula would have probably been more appropriate because we had not calculated the last term of the sequence. So if I plug this formula in as well, I'd still get 1,175. And that should be taken for granted. We should know that either should produce the same results. It's just the circumstances you might be presented with. uh, determine which one you want to use. And also, some people prefer to use the second formula because they remember it a lot easier. I mean, the first one has variables laid out differently, and this one has a little bit less variables, kind of more compact. People just find it sometimes easier to remember the second formula. The only drawback is that you have to make sure that you do calculate what this term is, and so you have to apply the previous formula to do that. Whichever case you find the easiest, that's what you want to go with, and so by all means, but I kind of go with the second one more often because it's not a big deal to calculate the nth term of the sequence if you know that formula. So now, geometric sequences or progressions. A geometric progression is a sequence of numbers in which each term after the first is obtained by multiplying the preceding term by a constant r. That constant r is known as the common ratio. So when we come up with a geometric progression or an arithmetic progression, we're taking the previous term and adding a constant each time as we go along. For a geometric progression, we're actually multiplying a constant as we move along. So if I have like a constant ratio of or common ratio of 2, I would take the first term, multiply that by 2, get my second term. Take the second term, multiply that by 2, get the next term. Obviously, if you're multiplying like that, you're going to get some really big numbers really quick. So oftentimes, for geometric progressions, you're going to see some big numbers both in finding a particular term of a sequence as well as finding the sum of a certain number of terms in that sequence. So the formula for calculating the nth term of a geometric progression is given by a sub n equals a times r to the n minus 1 power, where again a is the first term, r would be that common ratio, and n would be the position in, or the nth term, or how many terms in the sequence there are to get up to the number you're looking at. So use this formula in this circumstance here. Find the 15th term of the following sequence. 9, 15, 25. So you're given it as a geometric sequence. I can say it's not arithmetic because when I go from 9 to 15, that's a difference of 6. When I go from 15 to 25, that's a difference of 10. So I don't have a common difference. So we know it's geometric in this case. So how would you go about finding this answer? Pause a moment, answer the question you're going to be provided, and then we'll go over it. Okay, so we came to the conclusion that it's geometric, but sometimes, you have to make sure you discern the two, because sometimes you're just told, hey, here's a sequence, find the 15th term. And one of the things you're left to do is determine if it's arithmetic or geometric. Now, I mentioned before I gave the question for you to do that it wasn't arithmetic because I did not have a common difference. Does this have a common ratio? Well, when I look at this, I just show the formula, I notice that when I go from 15 divided by 9, that's if I reduce that, it's 5/3. Same thing if I go from 25 divided by 15. So for at least those first three terms, I have a common ratio, and I'm making the assumption from here on out that I'm following that common ratio throughout. So if I want to find the 15th term of this sequence, I'm going to take the first term, 9, times the common ratio, 5/3, and raise that ratio to the 15 minus 1 power. And when I compute that all out, I get about 11,484.84145. Oftentimes, you're going to need to round the numbers off because unless you have a common ratio that's an integer, you're going to get a lot of decimals at some point, especially as you move a little further along in the sequence. And you're going to get decimals that you may not necessarily be able to convert easily to fractions. So that's why you're going to see a lot of approximately equal signs for geometric progressions, especially when you're looking for like a term of a sequence that's like a 12th or 30th or things like that. Also, Under some circumstances, don't be surprised if your calculator starts throwing out some scientific notation to you, because the numbers in the geometric sequence can get quite big. The sum of the terms in a geometric progression. Now, since we're looking for a common ratio, we usually assume that r is always positive. Okay, a common difference could be positive or negative. Common ratios tend to just be positive, because if r is negative, that runs into some difficulties, because if r is negative for even powers of r, it's positive. For for odd powers, it would then still be negative, and that would be what we often call an alternating sequence, and that's not exactly a geometric progression. And it often causes issues on how to figure out the sum accurately. There are methods of doing it, but it's more complicated than using the formulas we have here. But so the circumstances we look at is if r is not equal to 1, it means that the common ratio is not 1. I use the formula a times 1 minus r to the n power all over 1 minus r to calculate the sum of that geometric sequence. If r happens to be 1, it just becomes n times a, because if, I'm going to basically have my common ratio is 1, and I'm going to have a sequence of all the same number. Like, the first term is, like, if I had the example from before where our first term was 9, if my sequence is 9, then, if I say, okay, well, if I want to figure out the first 15 terms of the sequence and what they add up to be, I'm just going to have 15 nines to have to figure out what that is, and then I can just multiply that together. For this example, though, we didn't have that. So now you're asked to find the sum of the first 15 terms of the following sequence. And notice there's only one formula for this. So it doesn't matter that we already know that, the 15th term was that value we found in the previous example. So, that doesn't mean anything to us. We don't really make use of that. We only have one formula here. So use that formula, see if you can compute the sum of the first 15 terms of this sequence. So using the formula, S of 15 equals 9 times 1 minus 5/3 to the 15th power, all over 1 minus 5/3. The 1 minus 5/3 to the 15th power comes approximately negative 2125.822491. And you deal with a lot of negatives on this, but they do cancel each other out because you're going to be dividing two negatives. So if I do 9 times that divided by negative 2/3, I get 28,698.6 approximately. And that would be the sum of the first 15 terms of the sequence. So again, just make sure you know the formulas for calculating a certain term of a sequence or progression, the sum of a certain number of terms in each progression. Make sure you know the difference between an arithmetic sequence and a geometric sequence, and don't confuse the formulas for them. Those are the common errors students make with that. The last thing to go over in this particular lesson is a method of depreciation, which is the double declining balance method of depreciation. It's basically just basically a way of depreciating. They go through a long explanation in the textbook as to like why one would want to use this. It's worth looking at, but the main idea is to make sure you know how to do it, not necessarily all the reasons why behind it would need to be done. But it might be worth something for you to look into to see like why would you want to do things this way. But if you're using this particular method of depreciation, V of n denotes the book value of an asset at the end of n years. Then the terms C, the original cost, V1, V2, Vn form a geometric progression with first term C and common ratio 1 minus 2 over capital N. The double declining balance method of depreciation usually is a depreciation model that can only be set for a finite amount of time. So, usually after you use that, you go to another method of depreciation, because if you keep using this, you end up with, um, saying that you have something that's worth a negative amount, which technically doesn't really mean anything. So your book value is negative. That doesn't make any sense for a book value. Um, so usually you define it for a certain period of time, and then you usually use another depreciation method, as you go along with that. So basically, the nth term, Vn, is given by this formula. So you have the formula Vn equals C times 1 minus 2 over capital N raised to the n power, where little n, lowercase n, is between 1 and capital N. So oftentimes you're going to say, we're applying this method for depreciation for X amount of time, and you're going to be looking for the book value at some term between those times. Also, D of n denotes the amount by which the asset has been depreciated by the end of the nth year. Again, they're giving you another formula that you really don't need to have. And the reason being for that is that, basically, if you know what the starting amount was, what it was originally worth, and you know what it is now, you don't need an extra formula to calculate, how much it's depreciated, because just take a difference. So you're going to notice I do not use this second formula at all. It's again one of those circumstances that your textbook just loves to have, and that's by giving you more formulas than you actually need. If you want to memorize the formula, you're more than welcome to do that, but I'm not going to use it, because this first formula, it's enough. And so when I ask this question here, a restaurant's equipment is purchased at a cost of $150,000, is to be depreciated by the double declining balance method over 10 years. What is the book value of the equipment at the end of 6 years? By what amount has the equipment been depreciated at the end of the 6th year? So there's two questions here. I want you to answer both, and then when we come back, then I'm going to go through this. All right, so we have this restaurant equipment. It's worth $150,000 right now. It's going to be depreciated using this method over a 10-year period. So we want to find out what the book value is at the end of 6 years and how much it's been depreciated at the end of 6 years. So the first part, what's the book value of the equipment at the end of 6 years? I'm just going to calculate V of 6. I'm just going to plug the numbers in. $150,000 worth right now. Capital N is 10, because that's how long we're going to be applying this method. We're looking for what's going on at year 6. So pretty straightforward. When I calculate this out, I get $39,321.60. So if I'm using this method of depreciation, the equipment that I bought for $150,000 6 years later has a book value of $39,321.60. The second question is asking by what amount has the equipment been depreciated at the end of the 6th year. Now again, they give you that formula that I crossed out over there, but I really don't need it, because the depreciation is just going to be $150,000 minus V of 6. So if I do $150,000 minus $39,321.60, I end up with $110,678.40. So that means the equipment depreciated by that amount, the $110,678.40, I didn't get the 40 cents down there, at the end of the 6th year. So, if you plug the numbers into the formula that you see over there, it should give you the same amount. So it doesn't matter if you use that method or not, if you want to use another formula, but again, it is another formula you have to memorize. And that brings us to the end of this particular topic and the end of Chapter 5 that we have to study. So if you have any further questions, please make sure to bring them up in class. Until next time, have a good day.